Very, very pleased to see here Peter Koellner, who is going to give a philosophical edge to what we do, and he'll tell us to the search for deep inconsistency. Thank you.
Thanks. Well, thanks to the organizers for inviting me. I'm going to be talking about the possibility of a deep inconsistency proof, and I'll explain what I mean by deep. So let's start at the beginning. We've got 0, 1, 2, 3. And the question is, how far does it go? So, we start along this path as children, this game, who can name the largest number. And some people stop, at different places. Some people stop at 6. And a young friend of mine explained why people stop at 6. Because 6 was afraid of 7, because 7, 8, 9. But children are fearless, and curiosity knows no bounds, so let's just keep going. So we can name larger and larger finite numbers, and some numbers that are familiar to you are the Google, and then there's the Googleplex. And when we're playing this game, we try to name numbers which completely transcend the previous number. You can't just keep adding 1. And then there's Skew's number and Graham's number, and you get these outrageously large finite numbers. And then when we pass to the infinite, things get really interesting, and again, the question is, how far does it go? There's a related question having to do with mathematical theories in general, and so I want to briefly explain that. So if you take the space of mathematical theories, they can be ordered under the relation of relative interpretability. So just as Gödel showed that you can interpret syntax in number theory, you've got this general relation of relative interpretability, and that's a precise notion. And according to that relation, the theories in general are chaotic. So they form neither a linear nor a well-founded ordering. You get incomparable points between any two theories you can interpolate. That's a result of Pfefferman. But remarkably, when you look at the theories that arise in mathematical practice, and not these artificially ones that you cook up, the theories all line up in a well-ordering. And there's a related question to the question, how far do the numbers go? There's the question, how far does this hierarchy go? And it's related because the canonical way to climb that hierarchy, the hierarchy of interpretability, also known as the hierarchy of consistency strength, is through principles of pure strength, and most notably large cardinal axioms. So we want to know these two things. How far do the large cardinal axioms go? And relatedly, how far does the hierarchy of interpretability go? So that's the question I'm going to focus on. That's really by way of motivation. And there's two other motivations. So the first is the one that I started off with at the beginning, just the intrinsic interest of this. How high can you count? And the second is the one I mentioned, to chart out the hierarchy of interpretability. And at a certain stage, when you start climbing the large cardinal hierarchy, you contradict the limitative principle of V equals L. So when you hit measurable cardinals, you contradict that principle. And the question is, are there stages which contradict other principles, like AC? And the third motivation is the search for deep inconsistency. So quite often people purport to show that weak theories are inconsistent. So a couple of years ago, Nelson thought he had a proof of the inconsistency of piano arithmetic. And there's, I think Weakly claims that ZF is inconsistent, measurable cardinals are inconsistent. And those proofs generally falter. And the ones that haven't faltered, like Kunin's inconsistency proof, which concerns a very strong system, they're pretty transparent. Where you can write down the proof on one page. So I'm interested in the question of whether there's a deep inconsistency, something you can't write down on one page, something that takes, 100 pages. It can't be shortened. Something that involves a lot of really deep structure theory. Okay, so I'll continue the review in the second section by just reminding you a bit about large cardinals. The large cardinals divide into the small and the large, and there's also the very large, which I'm going to be discussing today. So the defining characteristic of small large cardinals is that they're incompatible with V equals L. I'm just going to, pardon? Oh, that they're compatible, yeah. I'm just going to take that as my working definition. So some small large cardinals, there's inaccessible, mollow, weakly compact, indescribable, subtle, ineffable. And there's a natural template for generating these through reflection principles. So the general schematic form of a reflection principle says that if V satisfies a certain property, then there's a level that satisfies that property. And Scott showed that measurable cardinals are not small, according to that definition, so they imply V doesn't equal L. And some large cardinals, measurable, strong, supercompact, huge, rank to rank, and then I naught, which says that there's an elementary embedding from L of B lambda plus 1 to itself with critical point below lambda. And the template for generating those is in terms of elementary embeddings, which assert that there exists a non-trivial elementary embedding from J from V to M, where M is transitive class. So first I want to discuss simple inconsistency. So if you push these two templates, then you get an inconsistency in each direction, but it's a simple inconsistency. It's not a deep inconsistency. So let's look at the first template, reflection principles. So again, schematically, reflection principle says that if V satisfies phi of A, where A is an arbitrary parameter, then there exists a level of the universe, V alpha, that satisfies the same formula when you relativize all the quantifiers and you restrict the parameter down to the level V alpha. So this is the picture. You've got some higher order parameter A. V satisfies that phi holds of A. And the idea is that that can't characterize V. And the way of, because V is supposed to be indescribable, and the way that that's cashed out is by saying that what you've really done is you've unwittingly characterized an earlier level of the universe. So some V alpha is going to satisfy the relativized version of that formula with the relativized parameter. So if this has first order quantifiers, then you just restrict the quantifiers to ranging over this level. If it has second order, then it's the power set of that level, and so on. And if this is a first order parameter, it just gets reflected to itself. If it's a second order, you intersect it with V alpha, and then you iteratively continue. So I'm going to use x, y, and z as variables for the first order, and for m greater than 1, second and higher order, I'll just use a superscript m. And relativization for a second order parameter is just obtained by taking the intersection. So you take A and you intersect it with V beta. And for third and higher, that should be it, you take the set of the relativizations. So that's how we're relativizing parameters. And strength is obtained by moving to higher order languages and higher order parameters. So first you crank up the order of the language, and then keep your parameters second order, and then you try to crank up the order of your parameters. So some basic facts. If you look at reflection principles with first order formulas, then you get infinity and replacement, and you actually get an equivalence relative to the other axioms. And if you look at higher order parameters, higher order formulas with second order parameters, then using the reflection principle, you get inaccessibles, MALOs, weakly compact, indescribable, and so on. Okay, now if you move to third order parameters, then as Reinhardt pointed out, there's an immediate problem. You get an inconsistency right away, and it's just a one-line proof. So that's not a deep inconsistency. And one has to restrict the language to positive formulas. And by a positive formula, I mean one built up in the following way. You don't have negation. You have or and for all there exists. And the atoms have negation built in. So for the first order level, you've got negation. But then when you go to the higher, and at the second order level, you've got negation. But when you go to the higher level, you only have positive membership. So that's why this is called the collection of positive formulas. And Tate investigated this, and he showed that if you have a level of the universe that satisfies what's called gamma 2n reflection, I'm not defining that here, but it's based on these positive formulas. So you have the second level, the 2 indicates the level of the parameters, and the n indicates the level of alternation. Then you get the kappa is n ineffable. So Tate was able to get ineffable cardinals using this, and the question was how strong is gamma 2n reflection, and how strong are the stronger generalized reflection principles. And it turns out that they're weak, so if you have the Erdős cardinal kappa omega, there's a level that satisfies Tate's reflection, and so it's compatible with V equals L. So these reflection principles don't give you they don't give you large cardinals. And if you go to the next level, so this is the first level, that's consistent with V equals L, and then you can try going to the next level, but when you do that, at the next level, you get inconsistency. And the proof is a short one. It's just, a couple pages. It's not deep, but the deepest thing in it is probably Boder's theorem and some combinatorics. So that's not an example of a deep inconsistency. And then let's go to the large cardinals. So again, we have a template for generating them. The template says that there's a non-trivial elementary embedding J from V into M, where M is a transitive class. And strength is obtained by, the large cardinal associated with this is the critical point, the first ordinal moved. And strength is obtained by demanding that M resemble V more and more. So some milestones. If you have such an embedding, then necessarily V kappa plus 1 of M agrees with V kappa plus 1, and that's where you get measurables. If you demand that you have more agreement, like kappa plus 2 or up to lambda for some lambda, you get lambda strongs. And if you demand agreement in a different form, where you require not level by level agreement, but agreement in terms of closure, if you require that M be lambda closed, then you get lambda supercompact. And in the limit, the ultimate large cardinal axiom would involve the ultimate degree of resemblance, where you've got M equals V. And Reinhardt proposed this at the end of his dissertation. And then shortly thereafter, Koellner showed that if you assume AC, then there's no non-trivial elementary embedding J from V into V. Now, one thing that's interesting about this is that as you make M look more and more like V, you get more and more reflection. And then if you make M equal V, you'd think, well, you get just too much reflection and things collapse. But the actual proof of the inconsistency doesn't go that direction. It doesn't use the fact that you're getting too much reflection. And people have tried to get a proof which does have that general character, it makes essential use of the axiom of choice, and one way of viewing the proof is the way Wooden does, which uses Solovey's theorem on splitting stationary sets. So this is a more involved proof. It uses a pretty deep theorem, the Solovey theorem, under one version of it, but it's still a fairly straightforward proof. I mean, you can do it in a couple of pages, and so it's not what I'm calling a deep inconsistency. And it was also found right away, like, you know, Koellner found this just shortly after learning about it. Okay, so each template, when pursued far enough, leads to inconsistency, which is kind of unfortunate because if these templates are giving you a justification for the large cardinal axioms, you'd hope that they just worked all the way, and you want to have a good understanding of where they break down. But in each case, the inconsistency is simple. And in the search for a deep inconsistency, what we're going to do is we're going to turn to very large cardinals. So the small large cardinals are the ones that are compatible with V equals L, and the large cardinals are the ones that are compatible with AC. So large cardinals imply V doesn't equal L, but they're compatible with AC. And the very large cardinals imply AC fails. So yeah, in moving from small large cardinals, we broke the V equals L barrier, and now in moving to large cardinals, from large cardinals to very large cardinals, we'll break the AC barrier. So the picture is, you've got small large cardinal axioms, large cardinal axioms, very large cardinal axioms, and these are compatible with V equals L. Here, V doesn't equal L, but they're compatible with AC. And here you get not AC. So if you look at this picture and you see V equals L as a constructive limitative principle, and you also view AC as a constructive limitative principle, then what's happening is the large cardinals are shattering those constructive principles. They're saying the universe isn't as orderly as you thought. It's not L, doesn't even have choice. So this is the road to chaos. Okay, large cardinals beyond choice. So this is joint work with Joan Bagria and Hugh Wooden. Our hierarchy is going to start with the large cardinal that Koellner showed to be inconsistent with choice. So we're going to work in ZF, and some care is required in formulating the standard large cardinals when you don't have choice, but I'll just pass over that in silence. So we're going to turn that, now that we've dropped choice, we're going to embrace, just temporarily in the hope of finding a deep inconsistency, the things that Koellner showed don't exist when you have choice. So a cardinal kappa is a Reinhardt cardinal if there's a non-trivial elementary embedding J from V into V, and kappa is the critical point. And we're just working in ZF now.
But ZF doesn't have a second order quantifier, so what do you mean exactly? You work with ZF of J, I mean with J as a class predicate, or what?
I mean what you mean in the first section of your paper on this topic. You can either use, Gödel-Bernays, or you can use Morse-Kelley, or you can add J as a new constant. And, But I'm going to actually work in the second order context. So you'll see I'll start writing ZF sub 2, by which I mean Morse-Kelley, because I'm always going to be interested in levels V kappa that satisfy it. So a cardinal kappa is a super Reinhardt if for all ordinals lambda there exists a non-trivial elementary embedding J from V into V such that the critical point of J equals kappa, and kappa gets sent above lambda. So it's like the strong version of, it's like a strong cardinal. Okay, and there now you're quantifying over the j's. Okay, so what's the relation between these two? And the theorem is that if you have a super Reinhardt cardinal, then there exists a level v lambda such that v lambda and v lambda plus 1, so I'm using this to interpret the second order quantifiers, so we satisfy second order ZF, satisfies there's a Reinhardt cardinal. Okay, so that's good, right? Super Reinhardts on the face of it look like they're stronger than Reinhardts, and they are. A super Reinhardt cardinal rank reflects a Reinhardt cardinal. So this is what I mean by rank reflection. If you've got a cardinal kappa, then there's a rank level below which satisfies that the weaker large cardinal holds. Okay, so I'm going to zoom in on this region here. So we've got Reinhardt, now we've got super Reinhardt. And it'd be nice to show that a super Reinhardt actually reflected a Reinhardt, but that's open. So do super Reinhardts reflect Reinhardt cardinals? That is, if kappa is a super Reinhardt, must there be a Reinhardt cardinal below kappa? It's a very natural question. But, you know, when you don't have choice, things get weird. Okay, so now I'm going to move to the next level of the hierarchy, and there's variations on that. You know, there's a notion of a totally super Reinhardt cardinal, but I'm not going to go into the details. And then the next milestone is the Berkeley cardinal, but first we have to define a degenerate version, a proto-Berkeley cardinal. So for a transitive set M, let script E of M be the collection of all non-trivial elementary embeddings J from M to M. An ordinal delta is a proto-Berkeley cardinal if for any transitive set you take that contains it, that set is not going to be rigid. So there's going to be an embedding from that set into itself with critical point less than the ordinal. So this ordinal is so nasty that when you put it in a transitive set, it forces that transitive set to have an elementary embedding from it into itself with critical point below. So you're getting lots of embeddings from V lambdas to V lambdas, right? Like if delta is a Berkeley cardinal, just take any lambda above delta and look at V lambda, and then you're getting an embedding from that into itself. So you're spinning out all of these consequences of the Kunin theorem. But it's a degenerate notion because if delta is the least proto-Berkeley cardinal, then every ordinal greater than delta is also a proto-Berkeley cardinal. And you know, you don't want that. So what we want to do is we want to isolate the genuine Berkeley cardinals from the proto-Berkeley cardinals. And you do that with a theorem that's based on a lemma. So for the lemma says that for any set A, there exists a transitive set M such that A is in M and A is definable without parameters in M. And then the theorem is that if you look at the least proto-Berkeley cardinal, then you get that for all transitive sets, if they contain it, for all transitive sets that contain it, and for any ordinal less than it, there's going to be an elementary embedding such that the critical point is above that ordinal. So in other words, any set that contains it, if you look at the class of embeddings, their critical points go arbitrarily high in that ordinal. Now that's not going to be true of all of the degenerate Berkeley cardinals. It's not going to be true of all the proto ones. So we're just going to isolate that as our defining characteristic. So a cardinal delta is a Berkeley cardinal if for every transitive set M such that delta is in it, for every ordinal eta less than delta, there exists an embedding from M to M with critical point above eta and below delta. So this isolates the genuine Berkeley cardinals from the class of proto-Berkeley cardinals. Okay, so notice the least proto-Berkeley cardinal is a Berkeley cardinal. And if delta is a limit of Berkeley cardinals, then delta is a Berkeley cardinal. In other words, the class of Berkeley cardinals is closed. Okay, so lemma, if you take the least Berkeley cardinal, then for a tail of limit ordinals, beta, if there's an embedding from v beta to v beta with critical point less than delta naught, then that embedding has to send delta naught to itself, and there's going to be cofinally many fixed points. And this is a useful lemma because it allows you to show this. Suppose that delta naught's the least Berkeley cardinal, then there's going to be a level less than delta naught such that v gamma plus 1, I mean, I should have v gamma, comma, v gamma plus 1, satisfies second order ZF plus there's an extendable cardinal and there's a Reinhardt cardinal. So now we've got Berkeley cardinals, and we've got super Reinhardts rank reflect Berkeley, and Berkeley cardinals rank reflect, I mean, super Reinhardt rank reflect Reinhardt, and Berkeley cardinals rank reflect Reinhardt. So that's good. So you've got this. Unfortunately, we don't know the relation between these two. So what we're doing is we're mapping out the hierarchy of large cardinals beyond choice, and there's a lot of things that are unknown. Okay, so now I'm going to mention a conjecture due to Wooden, the Hogg conjecture. It says there's a proper class of regular cardinals lambda such that for all kappa less than lambda, if 2 to the kappa is computed in Hod is less than lambda, then there's a partition in Hod of the points below lambda of cofinality omega into stationary sets, where the partition has length kappa, for any kappa satisfying this property. So you're getting definable partitions into stationary sets. And when I was a graduate student, this conjecture went by a different name. It was called the silly conjecture. And it really does seem like an implausible conjecture. But there's been increasingly more evidence for it, and a lot of people now believe it. So it follows from the above theorem, this theorem says that a Berkeley cardinal rank reflects an extendable and a Reinhardt. Follows from that theorem and deep results of Wooden that if the Hogg conjecture is true, then there's no Berkeley cardinals. Now, there's very good reason to think that the Hogg conjecture, the silly conjecture, if true, has a very difficult proof. The evidence for it largely comes from intermodal theory. So there's a conjecture called the ultimate L conjecture of Wooden, which implies the Hogg conjecture, and the ultimate L conjecture is kind of like the holy grail of intermodal theory, and if there's going to be a proof of that, it's going to be very deep. So this would be an example of a deep inconsistency. Okay, but we don't know whether the Hogg conjecture is true or not, so let's just proceed upward. What we're trying to do is we're trying to get, so if the Hogg conjecture is true, then you wipe out Berkeley cardinals, and you wipe out actually super Reinhardts, and what you wipe out is you wipe out a Reinhardt plus an extendable. And that pretty much rules out Reinhardts as legitimate large cardinals, because if you've got a genuine large cardinal should be compatible with another genuine large cardinal. And so Reinhardt should be compatible with extendables. But the Hogg conjecture would wipe that out. So it essentially wipes out the choiceless hierarchy. So a cardinal delta is a club Berkeley cardinal if it's regular, and for all clubs contained in delta, and for all transitive sets M that contain B delta plus 1, there's an embedding from M into M where now you're getting that the critical point is in that chosen club. And here you do get rank reflection. So if you've got a club Berkeley cardinal, then you rank reflect as super Reinhardt. So above Berkeley cardinals, we have club Berkeley cardinals, and they rank reflect super Reinhardt. So things are lining up. There's still some unknowns in terms of the relation of rank reflection, and there's a lot of unknowns in terms of straight out reflection. Okay, so the next questions that arise are, one, whether it's possible to rank reflect a Berkeley cardinal, because what we've done is we've just rank reflected a super Reinhardt in the Berkeley hierarchy, and whether it's possible to have a Berkeley cardinal which is also extendable, or even better, super Reinhardt. And you actually can show that the least Berkeley cardinal can't be extendable. And the proof of that theorem, that lemma, motivates the notion implicit in here, which we're going to call a limit club Berkeley cardinal. So this is the strongest principle that we know of so far. And that rank reflects a Berkeley cardinal. So it's unfortunate the things that we know, we're skipping some connections. In fact, you get a level that satisfies that there's a Berkeley cardinal that's also a super Reinhardt. Okay, so I gave a list of the small large cardinals and the large cardinals, and then here's a list of the very large cardinals, some of the milestones. There's a lot of other things hidden in there, and it'd be of interest to find more, especially above a limit club Berkeley cardinal. So we've got Reinhardt, we've got super Reinhardt, we've got Berkeley, club Berkeley, and limit club Berkeley. And they're all getting stronger. And the thing that's known so far is that if the Hogg conjecture is true, then you wipe out Berkeley cardinals, you wipe out super Reinhardts, and you wipe out a Reinhardt as a genuine large cardinal notion insofar as you wipe out a Reinhardt plus an extendable. So if that conjecture holds, this whole hierarchy is a myth. There's good reason to believe that these things are inconsistent. But I'm a philosopher, and philosophers spend a lot of time investigating things that don't exist. But in this case, I'd be investigating things which one day we will know provably don't exist. Okay, so a very natural question is the cofinality of, for example, the least Berkeley cardinal. So I'm going to use delta naught to refer to the least Berkeley cardinal. I'm using it as a definite description. I'm not using it as a name. Okay, so I'm going to be evaluating delta naught in different universes. V of G for generic extension, and it's going to change its value. So must it be regular? Now you would think it had better be regular, right? It's a genuine large cardinal notion. But we don't have choice. The worst possibility would be that it could have cofinality omega. And that's connected with the question of choice, because you can prove the following theorem. If delta naught's the least Berkeley cardinal, and it turns out that its cofinality is gamma, then you get a failure of gamma DC. So in particular, if its cofinality is omega, then DC fails. So that would be a really radical violation of choice, right? I mean, we're not just throwing away AC. In the case where the cofinality is omega, you're throwing away DC. And, I mean, the universe looks weird without AC, but it looks really weird without DC. And a lot of people would think that DC is just an evident principle. So if you're violating DC, then yeah, a lot of people think AC is an evident principle, but even more people think that DC is an evident principle. Okay, so suppose that delta naught. So these are preliminary results here. They've been superseded. We showed that if delta is a club Berkeley cardinal, which is a limit of club Berkeley cardinals, in other words, if it's a limit club Berkeley cardinal, then there's a forcing extension, which is a prickly forcing in the context of ZF, such that it satisfies the cofinality equals omega. And it's a really, this is a very involved proof. The trick is showing that you, when you do the prickly forcing, the trick is showing that you preserve the Berkeley cardinal. And what happens is you might actually, you don't know that you preserve the Berkeley cardinal. The least Berkeley cardinal might have changed. But then you just make it cofinality omega and you keep iterating. So and then it's got to stop at some point. And then this is a different slide. Can you see the difference? So you can also get that the cofinality is greater than omega. But these results were recently improved by our student, Raffaella Cutolo. She showed that you can simplify it considerably. You don't need the club Berkeley cardinal. Whoops. If you just have ZF plus DC and a Berkeley cardinal, then there's a forcing extension V of G, which makes the cofinality omega 1. Now, if you've got DC, the cofinality has to be greater than omega by that earlier result, but this is pinning it down to be omega 1. Okay? And then there's a related result. If you just have a Berkeley cardinal, then you can force to get the cofinality omega. So this is an unfortunate situation, right? You would think that with these large cardinal notions, the cofinality shouldn't be omega, and you would also think that it shouldn't be undecidable what the cofinality is. I mean, if it's undecidable, how are you going to figure it out? But it turns out that it's undecidable. So you've got radical independence appearing at this level, and that might make one suspicious. So you might think, perhaps there's an inconsistency lurking below the surface. Okay, so I want to mention two plausible hypotheses concerning the cofinality of the least Berkeley cardinal, each of which, true, would lead to a new inconsistency result. So this talk was called The Search for a Deep Inconsistency, right? I hope you didn't think that I was going to actually give you a deep inconsistency. I'm just giving you some pointers in the direction of where you might find one, if you're looking for that sort of thing. So we saw that the cofinality of delta naught is independent. We also saw that the cofinality of delta naught, the least Berkeley cardinal, is connected with the failure of choice. The lower the cofinality, the greater the failure of choice. Now, since these principles are violating AC, it seems that you obtain stronger and stronger principles by folding in more and more AC. There's this, tension between the principle and AC. And what you want to do is you want to put in more AC, and you would expect that you get a stronger inconsistency, a stronger principle. So that intuition would lead to this hierarchy. You have ZF plus, there's a Berkeley cardinal, plus the cofinality of the least Berkeley cardinal is omega. ZF plus there's a Berkeley cardinal plus DC, plus the cofinality is omega 1. So you keep putting in more and more DC, necessarily you're increasing the cofinality, but you're also adding that you increase it to just the minimal amount that you require. And the hope is that this is a hierarchy, but it's very hard to see how you could do anything in terms of showing that this is a hierarchy. So if it is indeed a hierarchy of stronger and stronger principles, then one would expect this, that if you demand that the cofinality be greater than omega, then that stronger principle would rank reflect the weaker principle. Okay, so call that plausible hypothesis 1. Plausible hypothesis 1 implies the inconsistency of ZF plus Berkeley cardinal plus DC. So that's just, that's a very weak plausibility argument. Now, if there's a genuine hierarchy here, as you would expect, then you articulate it in terms of this plausible principle. That gives you inconsistency. So that might be one way of getting a deep inconsistency. Establish the plausible principle. The depth of this inconsistency is going to be measured by the depth of that proof. I mean, if the plausible principle had I say it would be a moderately deep inconsistency. By that I just mean that this theorem is not a deep theorem. But if the proof of the plausible hypothesis was, took like 3,000 pages and couldn't be shortened, then this would be a deep inconsistency.
So is the theorem that if the plausible hypothesis is provable, or
if it's true, yeah.
If it's true, then you get the inconsistency.
Yeah. But plausible hypothesis number 1 might fail because of another plausible hypothesis, namely that you can actually prove that the cofinality is itself. So you can prove that Berkeley cardinals are necessarily regular. And again, that implies the inconsistency of ZF plus a Berkeley cardinal because of the forcing theorem. And I say this would constitute a genuinely deep inconsistency, but by that I just mean that this is a fairly, the forcing theorem involved here is a fairly deep theorem. It could be a really deep theorem if the proof of the plausible hypothesis was deep. Okay, so the summary is that plausible hypothesis 1 points toward a moderately deep inconsistency and possibly a really deep one. Plausible hypothesis 2 points to a genuine deep inconsistency, possibly a really deep one. And the Hogg conjecture points to a very deep inconsistency because there's good reason to think that the Hogg conjecture the proof of it is going to be hard. And it's a conjecture of ZFC. Okay, so I want to close by mentioning 2 futures based on the work of Roger Zelazny. Future 1 is pattern. So this is where pattern prevails. The first is that intermodal theory succeeds. And by this I mean that intermodal theory reaches 1 supercompact. So Wooden has shown that if you can push intermodal theory to 1 supercompact, then there's this overflow phenomenon where the resulting intermodal absorbs all the large cardinals that are in the larger universe. So if intermodal theory succeeds to 1 supercompact or all the way, that would be great. And one way of articulating that is in terms of Wooden's ultimate V equals ultimate L conjecture. This is all part of the same nice package. The ultimate L V equals ultimate L conjecture implies the Hogg conjecture, so in this we have the Hogg conjecture holds. And large cardinals beyond choice. Oh. What did I do? Large cardinals beyond choice. That's a limit club Berkeley cardinal. Oh. Yeah, that's a coincidence that I just realized. Large cardinals beyond choice. So this is even stronger than limit club Berkeley cardinals are inconsistent. This is all large cardinals beyond choice are inconsistent. And then the second future is the future where chaos prevails. That's where large cardinals beyond choice are consistent and the Hogg conjecture fails, the V equals ultimate L conjecture fails, and intermodal theory fails. So that would be a really weird universe to be in. What your take on it, I mean, we can discuss this in the question period, is going to be, depends on how firmly you believe choice. But just to give some motivation for this, suppose that it turned out that the large cardinals beyond choice were consistent, and the hierarchy of interpretability went really far, and the only way to climb it was if you violated AC. Wouldn't it then be plausible to view AC like one views V equals L as a limiting principle? What if it turned out that the large cardinals beyond choice implied that there were really remarkable structures? So if you have large cardinals beyond choice, then they're going to induce really powerful large cardinals within HOD. So we're in a chaotic world where we've got large cardinals beyond choice, Berkeley, Club Berkeley, limit Club Berkeley, and then you look at the HOD of that world. That's going to be a nice model of ZFC. Well, not so nice because intermodal theory is failing in this scenario, but it's nicer than the chaotic world on the outside. And you're going to get large cardinals in there. So you're going to have an embedding from HOD into HOD. You're going to have, that's what we might call a HOD-Reinhardt cardinal. You're going to have a HOD super-Reinhardt cardinal. That's a cardinal kappa, such that for every lambda, there's an embedding J from HOD to HOD, critical point kappa that gets shot above lambda. You're going to have HOD Berkeley cardinals, HOD Club Berkeley cardinals. You can formulate what these are. They're all going to start existing in the HOD. And what if it turned out that there was a lot of really incredible structure there that you couldn't see without invoking these principles on the outside that violated choice? So it would be a very weird situation to be in, and so we're hoping that that doesn't happen. And I think most people are banking on future one, the future of pattern, and that's why it's important to look for one of these inconsistency proofs, because you want to wipe out future two. Okay, thanks.
Just to challenge your chronology for Kuhnen's inconsistency, Reinhardt's thesis, a draft reached form in 1967. I think it was the summer of '69 that Kuhnen I received the proof of agreement.
Yeah.
There was a 2-year gap. It wasn't next week.
No. Yeah, you're right. I should have said that.
Yes.
So I actually have two questions. Could you back one slide to future number 2? I see you've got the statements there numbered, and I can't make out whether the numbering is just chaos or whether there's some significance there.
Yeah, that's it really is a chaotic future.
A slightly more serious question. Am I right in assuming that all of these large cardinals would be impervious to small forcing?
We don't know that. So with the Berkeley cardinal, that was a problem. Well, wait. No, it was just the prick reforcing that was a problem, right? Yeah, I don't know about that.
What I'm really getting at is
If you do force DC, so if you have an extendable, you can force DC. So if you have a Berkeley cardinal and extendable, you can force DC and you preserve the Berkeley cardinal.
But don't all the embeddings just live through the small forcing as long as the critical point is both sides of the forcing? Anyways, that's a very general, powerful argument. It seems like it should show that if you have the Berkeley cardinal in the ground model and you do small forcing, then all of the embeddings are going to lift that you wanted, and that would witness the property in the extension.
Probably right. I'm just cautious because there's no choice.
Yeah, I don't know. I mean, I don't know much about these things, but is it conceivable that some of these very large cardinals would have consequences for sets of low rank?
For example, if there's some deterministic connection.
Yeah, there is a connection with. That's a difficult question. don't know whether it's plausible. There is a connection with determinacy, though. So the first proof of definable determinacy, ADL of R, used choiceless large cardinals, so things that we now think are inconsistent. This was due to Wooden, I think, in '83. And then it was bumped down to V equals, it was bumped down to I naught. So you get ADL of R from I naught. But at first he was using inconsistent principles. So he was using this hierarchy to get a consequence concerning determinacy. Then it was bumped down, and then by Martin and Steele, the proof of PD was bumped down to the level of Wooden cardinals, and then the proof of ADL of R was bumped down to the level of Wooden cardinals, and then you get outright equivalence. There's another connection with determinacy that's probably worth mentioning. So it's very natural to look at the Hod of L of R in the context of determinacy. And we know that in that context, certain cardinals they look really large in Hod. So omega 1 looks like a measurable cardinal. So maybe omega 1 looks like a Berkeley cardinal. And you have to be a little careful in describing what it means to say that it looks like a Berkeley cardinal. So by that I mean precisely, it looks like a Berkeley cardinal with respect to transitive structures that live in Hod up to theta. Okay, so for every transitive structure that lives in a Hod up to theta that contains omega 1, you're going to have an embedding from it into itself, which lives in Hod. So the conjecture is that if you have ADL of R, then that's true. And then conversely, that if you have the statement that omega 1 in Hod of L of R is a Berkeley cardinal, for structures up to theta, then you get back ADL of R. So it could be, even if it turns out that this whole hierarchy gets wiped out, the first point I'm making is that it's been useful to look at this hierarchy as a guide to genuine theorems. First, because of the first, proof of definable determinacy, it used this hierarchy. And then second, because if this hierarchy gets wiped out, then you can still have restricted versions of these notions. So you can have the notion of a Hod Reinhardt, a Hod super Reinhardt, a Hod Berkeley cardinal, and that may prove to be useful.
I want to ask you about the second future, because it seems to me that's much more likely that we are in the second future. But how could we ever know?
The second future?
Yes.
So you think those things might be consistent?
It seems to be, philosophically speaking, much more likely, but I don't see how we could verify that if we are in the second future, we don't have any.
Yeah, we won't know. We'll just always worry about it, I guess.
But we're in it already, right?
Yes, but we won't know. Very little. Yes, Andrew.
Do you know that it's relatively consistent that the least Berkeley cardinal is regular?
No.
Marty, no, was it Martin that was the question? Did you have that?
I have maybe a shallow comment about. I mean, I like depth because for aesthetic reasons and maybe other reasons, but I think I want to somehow defend shallow inconsistencies because these mark the borders of the universe that we really understand very well.
Yeah.
I mean, shallow is good in the sense that it's not really shallow because Kuhn is inconsistency. You have to go through several chapters of Yek to understand it. It's shallow at our level. So shallow means that
I think it is a very relative statement.
it's a relative statement, and shallow means we have really understood it. So that's a good thing also.
Yeah, so the picture that I am intrigued by is this, that you get a proof that these are inconsistent. And it's, it's pretty short. And then you get a proof that these are inconsistent, and it's harder. And it gets harder as you approach the border. And then from the bottom, you're building inner models that are giving evidence for the consistency of the large cardinals. So you're approaching the border of inconsistency from two directions by getting more and more complicated inner models that certify the consistency. and then by from above by getting more and more complicated results showing inconsistency. And that seems to me like a plausible way things could go. So I agree that the simple points, like V equals L is a nice simple inner model, and the proof of the Reinhardt inconsistency is a simple one, but what you want is you want to, it's plausible to me that as you approach the border, you're going to get more and more, things are going to get more and more complicated.
Maybe you answered it, but I mean, imagine that Kunin's first proof of the inconsistency was 100 pages long instead, and he only found his shorter proof later. But if we had your understanding of what it means to be a deep inconsistency, we would have said that's a deep inconsistency at first, and then realized afterwards, oh, actually, it's much simpler.
Yeah, that's why I added that it couldn't be shortened.
And is it really correct to measure the deepness of an inconsistency result by how long or hard the proof?
No, of course not. No, it's a vague term. Yeah.
Okay, any other questions? Yes?
Yes, I would like to know, is there any case known where you actually climbed in the hierarchy of relative interpretability by adding choice? I mean, that's you speculated on that on one slide, but it's still a speculation, right?
It'd be where you can only climb by violating choice.
Yeah, I mean, you have a theory and sort of you add some amount of choice to it, and then it's stronger.
Okay. So that's where you're adding a bit of choice to the choiceless large cardinals. Yeah. No, nothing's known about that, and it's hard to see how you could prove those results, how you could establish those relations. So things in this hierarchy. There's a lot of stuff that can be figured out, I'm sure, getting these other connections, but figuring out the cofinality and stuff like that looks really hard. So hopefully all those questions will go away because all of these objects will go away.
The Reinhardt cardinals were the smallest large cardinals you consider. Is it not possible to try to find some large cardinal below?
Oh yeah, like an embedding from V lambda plus 2 into itself. Yeah, there are things below here that are inconsistent with choice. I'm just picking milestones, and there's things in between too.
Yes.
In general with these, is there a point of choice that it's obviously inconsistent? I mean, like in the case of I0, for instance, or lambda sort of you could talk about lambda DC and about that. That's where the choice becomes important. But with these, is there a point, where you could add choice up to that point, say the critical point, and it isn't obviously inconsistent?
No. The proof that choice fails in that context is pretty difficult because it goes through the solidate theorem. And the proof that choice fails when you've got cofinality equal omega, the proof that DC fails when you've got cofinality omega is much easier. So as you go up in strength, the proof that choice fails gets simpler.
Thanks, Peter. I think that this discussion is lovely, and you have set a very good example to leave some time at the end of your talk for discussion. That's very good. But I think we have to press on to the next speaker, so thank you very much.